Okay, on to week 2, when we really start to get into the foundations, laying the foundations for a better understanding of the special theory of relativity. So our theme for the week is events, clocks, and reference frames. I want to start off in this short video clip, however, just to remind ourselves where we've been. Last week we talked about Einstein in context. We got a better idea of the context of physics and science and technology in the 1800s, leading up to Einstein's own time in the late 1800s, early 1900s. A lot of things going on, as we saw. We also saw Einstein himself, his own life as a youth, and then especially at the university, and in the few years after, struggles he went through personally in terms of academics to a certain extent, although he certainly was a very good student, but certainly girlfriend problems, family problems, problems of finding a job, and so on and so forth. So it wasn't an easy time, certainly, for Einstein himself in these years around 1900. We also talked a little bit about his so-called miracle year of 1905, and saw how, even though it was an extraordinary output, perhaps the greatest year any scientist has ever had, you could certainly put it right up there with almost anything else, and yet there'd been a long period of preparation, probably at least 8 to 10 years when he'd been thinking about a lot of these problems. He'd been studying physics intensively. He'd been discussing it and almost everything else under the sun, philosophy, literature, science, with a couple of his friends in the Olympia Academy, for example, and with others as well. So there'd been that period of preparation before, in a sense, he burst on the scene in 1905. He'd also published a couple of papers even before 1905, which were pretty good efforts. In fact, you may have heard of the so-called 10-year rule or 10,000-hour rule, in that if you look at the actual lives of so-called child geniuses or prodigies, that one thing that characterizes them is they really have a real passion and drive for a given subject. And Einstein, probably not sure we'd call him a child prodigy, but certainly up there in the genius level in terms of his scientific achievements, and at a relatively young age. And it didn't just come out of nowhere, even though it seems that way, this unknown patent clerk, 26 years old in 1905. But he'd put in his roughly 10 years, 10,000 hours of really passionate study of these subjects. And then those insights came. So it was not necessarily an easy process. It was a lot of struggle at times, and perseverance, and pushing through to the final insight. So just Einstein in context, remember some of those things. Also just want to mention the quotes of the week. They are on your handout, but one of them is Einstein, of course. "It can scarcely be denied," he said, "that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible without having to surrender the adequate representation of a single datum of experience." Well, sort of a lot of words in there. This is probably the origin of another so-called quote by Einstein that you may have seen, and that is, "Everything should be as simple as possible, but no simpler." As far as we can tell, that appeared in Reader's Digest about 1977 or so, attributed to Einstein. It's unclear whether he actually ever said it in those words, but he certainly said things very, very close to that in this quotation, even though a little wordy, is one of those examples. So again, everything should be as simple as possible, but no simpler. This actually goes back to a concept that you may have heard about. Occasionally it comes up in conversation, called Occam's razor. And this goes back to a person named William Occam, spelled actually, we'll say William of Occam, who lived in the first part of the 1300s, medieval philosopher and scholar. He actually never stated it quite like it often is stated. The essential idea here is you don't want to multiply hypotheses unnecessarily. You want to try to explain things in as simple manner as possible, but it doesn't mean the simplest possible, because you want explanatory power as well. If something is so simple that it can't explain a certain range of experience, that something else that's maybe more complicated, a theory or idea that's more complicated, can explain it, then you want the one that has more explanatory power behind it. But everything else being equal, you try to make things as simple as possible. So sometimes called Occam's razor. In science, and especially in physics per se, the idea is that you want to just try to make your explanations as simple as possible. Don't multiply unnecessary assumptions or hypotheses and things like that. So that's, again, this idea, everything should be as simple as possible, but no simpler. Again, one of those quotes that you'll see all over the place attributed to Einstein, but a lot of people have said similar things over the years. Even before William of Ockham, there were, going all the way back to some of the Greek scholars, Ptolemy, for example, said something very, very similar to that. Another quote from Einstein, "Our experience hitherto justifies us in believing that nature is the realization of the simplest conceivable mathematical ideas. I am convinced that we can discover by means of purely mathematical constructions, by pure thought in a sense, the concepts and the laws connecting them with each other, which furnish the key to understanding of natural phenomena." This is a very interesting idea, and it sometimes goes under the heading of the unreasonable effectiveness of mathematics. The unreasonable effectiveness of mathematics. How is it that math is so successful, our math is so successful in describing the world, physical reality, in nature, especially in the field of physics? Why should it be that way? Einstein essentially is taking as an article of faith that it is, and that just by examining things mathematically and thinking mathematically, we can actually get at the essence of nature. Now, I asked you in sort of the engaging the brain portion of thinking about these quotations, think, is that really true? What would be some counterpoints to that? He certainly leaves out the whole idea of the importance of experimentation and experiments to verify things. Another thing that we talk about here, just put it down here, we talked about the unreasonable effectiveness of mathematics. A lot of physicists like to talk about beauty. They search for beauty in their equations. Einstein never quite said it like that, but he too also was looking for equations that were, in a sense, beautiful. There's another Nobel Prize winner named Paul Dirac, who later on, sort of the generation after Einstein, they were contemporaneous, but he's a little younger than Einstein, in the late 1920s, he applied relativity to the new theory of quantum mechanics and came out with a relativistic version of quantum mechanics. He applied the special theory of relativity to quantum mechanics. And he was very famous for always saying, I look for beauty in my equations. That's how I know they're true. Well, yes, but there are many cases where beauty sort of can lead one astray. Looking for very beautiful equations, very symmetrical equations that seem this is fantastic stuff, but does it actually match reality? So there's room for debate there, but certainly it is amazing the unreasonable effectiveness of mathematics in enabling us to describe successfully, sometimes very successfully. We have certain theories. There's a theory known as quantum electrodynamics. Okay, it was developed in the 1930s and into the 1940s as well, late 1940s, where theory predicts certain values to 8 or 9 decimal places. An experiment verifies that. That's absolutely astounding that we can do that to 8 or 9 decimal places, and every single decimal place is right when we actually do the measurements. So, something to ponder there. One other quotation here. To punish me for my contempt of authority, fate has made me an authority myself. And this is sort of a reminder that all those quotations you see floating around that are attributed to Einstein, like this, everything should be as simple as possible, but no simpler, may not actually be a real quotation from Einstein. So just the fact that he's the authority, if you put his name on something that sounds good, then people think, oh, Einstein said it, then it must be true. It must be something to follow there. So, a few quotes of the week. Thought experiment I want you to work on, the challenge of synchronization. We'll be talking about that more in one of the video clips, but it just sort of gets the mental juices flowing there to think about that thought experiment. So it's on the handout. You can read about that. And then a reading. I want you, especially those of you who are doing the quantitative approach, to read Einstein's paper that developed the early version of the special theory of relativity on the electrodynamics of moving bodies. I don't want you to understand the math or the physics involved. You don't have to do that. But just outline it. Summarize. What are the key points he's trying to make? Because there's a lot of points there where he just summarizes, okay, in this section we're going to do this, and now we're going to do this, and so on and so forth. If you're taking the more qualitative approach, recommend reading it and doing that same outline, get a sense of what he's trying to do in this paper. But we'll talk more about that as well later on. So that's themes for week 2, events, clocks, and reference frames. And then think about some of these larger issues that these quotes bring up as well, perhaps as we go along and as we start really constructing our understanding of the special theory of relativity. Okay, let's get started now with some concepts that are fundamental to the special theory of relativity. And in fact, as you can see here, events, clocks, and observers, they're almost trivial in a sense, and yet part of Einstein's great genius was to look at some of these key concepts that most people had just taken for granted and look at them in a new way and say, there's something here we really need to think more deeply about. And so that's what we want to start doing here. Remember, as we talked about in a previous video clip, that learning, gaining new knowledge is like a construction process. So what we're doing here is really laying those solid foundations. And even if you think, this is just pretty easy stuff, it's trivial, it's important to make sure we get those foundations laid firmly, because in my experience, if you don't do that, later on you'll encounter some things that won't quite make sense, and you'll suddenly realize, my foundations of my knowledge edifice, as it were, I'm working up here on the 5th floor, and all of a sudden I realize, the first floor, the basement maybe, isn't quite as solid as I thought it was. So, events, clocks, and observers. And another principle will follow here. You may remember from one of our previous video clips is festina lente, Latin for make haste slowly. So we're not going to try to speed along here. For those of you who think maybe we're going a little too slowly, certainly you can fast forward to through these parts and get to the end of it. But again, I'd encourage you not to assume too much. Just make sure that you really have that solid knowledge that we need. So, events, clocks, and observers, part 1 of this. We want to start by asking the question, what does it mean to observe something? And in particular, obviously, we could observe something and you could write down everything you see. We're going to focus, though, on 2 things. Basically, where something happened and when something happened. Okay? So we want, if there's a given event, and our standard event will be like a flash bulb going off or some sort of flash occurring at a particular location and time, and we want to specify that location in space and in time. And so typically, we talk about a 3-dimensional coordinate system. And don't worry if you haven't had this for a while. We're not going to do too much in 3 dimensions. But we want to do the general case first, and then we'll do simpler cases as we go along. But if we were going to create a 3-dimensional coordinate system, trying to draw it on a 2-dimensional board, we typically draw it like this, where we say this is the x-axis, the y-axis, and the z-axis. And clearly we need some sort of measuring system. We won't go into the details of how you might construct such a system, but obviously we have things like this, meter sticks or yardsticks, inches, meters, millimeters, centimeters, whatever, for our measuring system. And so in this case, we have the y-axis and the z-axis, and then the x-axis we have to imagine actually is coming out of the board here. And so we can specify any given point in that 3-dimensional space. If we put some tick marks on our axes here, we won't actually number them in this case, but here are the x tick marks. And then any given event would have an x-coordinate, a y-coordinate, and a z-coordinate. And so we could specify maybe the x-coordinate is 1, 2, 3. And so we'd come over here and maybe right here. And the y-coordinate 1, 2, 3, 4. And so, whoops, actually really looks like this. I went a little too far there. Okay, so that would be x-coordinate 3, y-coordinate 1, 2, 3, 4, and then maybe the z-coordinate someplace way up here. And this is where we have to use a little bit of our imagination to imagine it in 3 dimensions. So there is our event. So this is, here's the xy plane, and then some event with some z-coordinate in the vertical dimension there. Okay, so we talk about an event happening at x, y, and z. Clearly, though, we talked about not only where it's happening, but when it's happening. And so we need a time as well, and that's where clearly we have to have a system of time keeping. We've got our typical clocks that we have standard time with, and again, we're not going to go into the details of how you create a time-keeping system. We'll just assume that we have one, and it works pretty well. But for any given event, not only the location where it happens, but when it happens. So in fact, in addition to x, y, and z, we have one more coordinate to specify, and that's the time coordinate, t. And by the way, this is where the idea of time as the fourth dimension, which you hear about in a lot of science fiction movies and the like, actually comes from. It's not maybe as profound as it might seem to be in those science fiction movies. It's essentially just that we're marking an event, we're specifying an event with its 3 spatial coordinates, because we live in a 3-dimensional world, x, y, and z, and then its time as well, what time it actually happens. Now, one thing this presupposes is we have an origin right here. And our origin is arbitrary. We could set the origin here. We could set the origin over here. Whatever system we set up, whatever coordinate system we set up, we'll specify some origin. For our purposes, usually the origin will be where we have an observer. So here's our observer at the origin. This person then can mark off things in the x direction, y direction, z direction, obviously negative directions as well. I didn't draw those in because it gets a little messy on the board here. So they're at the origin. They are at point. You could say the origin is point x equals 0, y equals 0, z equals 0, and also time equals 0. That would be the time origin as well. So that really gets to the question of, how do we measure time here? How do we measure the time of this? Say there's a flash here. We'll just say it's some sort of flash bulb that goes off at that point in time. And maybe it's not, obviously it's not at 0, 0, 0. We said it was x equals 3, y equals 4, z equals 5 or so, something like that. So it'd be 3, 4, 5. And then at some given time, how are we going to record that time? Well, we could imagine that the observer here has a clock at the origin, a clock that keeps good time and is synchronized to some timekeeping system. And therefore, when that flash goes off and the observer sees that flash, they could record the time on their clock. There's a little bit of a problem with that, as you probably immediately see here. Something that you may know about, we haven't officially covered it yet, but light does not move at infinite speed. It moves at a finite speed. So when this flash goes off here, and let me see if I've got my red pen in here someplace. Well, we'll try green a little bit here. So it's green light in this case. So the flash the light from that flash takes a while to get to where our observer is at the origin. And so they record the time on their clock at that point, but clearly that time is a little bit after when the flash actually occurred. And clearly we could figure out what this distance was. Light moves at a constant velocity. Again, something we haven't officially covered yet, but you may know that. We will just assume it for the moment, that we know what the speed of light is. If we know the x, y, and z coordinates, we can figure out this distance here. It's really just the Pythagorean theorem really in 3 dimensions, which we won't bother with, but if you're interested in that. So we could figure out this distance. We could figure out, given the time recorded at the origin, we could backtrack and figure out exactly when it occurred here. So that clearly would be one way of doing this. But there's actually another way we're going to do, or actually let me just mention two other ways. One we'll use and one we won't. We could say, just to make things easier, why not put the clocks all over the place? In other words, why not have every point in our three-dimensional space have its own little clock by it? We'll assume we can do that. There are imaginary clocks here, so that when this flash goes off, there's actually a clock right there. So we can record not only the x, y, and z coordinates, the three-dimensional coordinates, but the time. In fact, we're going to call this a principle, and we'll call it the photo clock principle. The photo clock principle, or sometimes we'll just say the clock principle. Here's the idea. We're going to imagine that every single point in time has a clock associated with it. And all we have to do to find out when something happens, okay, we'll just see the flash of light, our standard event that we're using here, and we'll assume that when that flash of light goes off, there's a photo taken along with the clock time. So this is just a time clock, and photo taken, it records the location of the clock, the XYZ location, and the time that is showing on the clock at that instant. So we'll call that the photo clock principle. You might say, well, that's pretty common sense in a way, and what's the big deal about that? Well, we'll see this is going to be a really key idea when we work with some of the principles and results of the special theory of relativity. So that's why we're introducing it now. Again, to summarize, we're going to record an event, its location in space and time, where and when it happened, not only with its x, y, z coordinates, but with a clock located right at those x, y, and z coordinates. So we'll assume that every x, y, z point in our three-dimensional space has a little imaginary clock right there, and we can record that time. So really, you imagine, we'll sometimes call it a lattice of clocks, or sometimes we'll call it a grid of clocks. Use those terms interchangeably. So a lattice of clocks, you can imagine this three-dimensional space, and every single point has a clock associated with it. Or so it's a lattice of clocks, or this grid of clocks, so that for any given flash that may occur in our three-dimensional space, we just look at the nearest clock there that will take its picture and record the XYZ coordinates and the time showing on that clock at that instant of the flash. Now, for those of you who might be saying, well, there are an infinite number of points here. We're going to have an infinite number of clocks. In principle, we could, but we'll just say that depending on how precise we want our timekeeping to be and our XYZ coordinates to be, we can also make the clocks closer and closer together. So again, these are imaginary clocks. And we'll just assume that we have enough clocks and at enough points in space, and they're close enough together to record the where and when, the space-time location, the XYZ coordinates, and the time of any given event that we want. So that's the idea of an event. It's just we wanted to look at the where and when, the space and time location of the event. What that means then is to observe an event, and we'll often talk about observing an event, seeing an event happen. For our purposes in this class, what that will mean is we will record it using the photo clock principle. In other words, there's a clock, an imaginary clock at that point that we know its XYZ coordinates of that clock, and then flash photo goes off, it records the time, and that will give us the XYZT coordinates of a given event using the photo clock principle, or sometimes we'll just say the clock principle for that. Okay, so that's the basic idea of an event occurring, how clocks come into it, this lattice or grid of clocks. What an observer is, again, the observer is at the origin here, but the observer has their whole lattice and grid of clocks. And you can say, well, when the event actually occurs, they actually haven't seen it yet. The light hasn't reached them if it's far enough away. Even if it's not that far away, technically it hasn't reached them yet. Light goes very fast, of course, so essentially for common day experiences and events, it's nearly instantaneous, or instantaneous as far as we can can tell in our everyday experience. But what does it mean to observe it? What it means for this observer is the flash goes off, the clock takes the photo of it, there's a photo taken of the clock, and then the observer can go back later and look at the recording of that and say, okay, it happened at X, Y, Z, those coordinates, and time t. So that's what it means to observe an event. We will use this clock principle to do that. Now, having said all that, we've glossed over one point. I'm sure many of you are thinking, well, wait a minute, what about the fact of synchronization, or the problem, challenge of synchronization here? We've got this whole lattice grid of clocks all over the place at every given point we're interested in here. How do we know they're all synchronized with each other? And so that's going to be our subject of our Part 2 video clip on events, clocks, and observers. All right, we ended the last video clip, which was on Part 1 of events, clocks, and observers. We are talking about a lattice or a grid of clocks that we're going to use to specify when something happens. Not only when, but where. So we'll have a clock at every location in space, say 3 dimensions, and then using a photo device, whenever an event occurs at that location, photo will be taken that records not only the location of the event in X, Y, Z coordinates, but also the time on the clock at that location. But it raises the question of how do we synchronize the clocks? How do we make sure they're synchronized? And so that's what we're going to work on in this video clip. We've reduced it just to 1 dimension now. As I mentioned last time, we did 3 dimensions last time just to get the general concept. From now on, we'll be working in 1 dimension. So we just have the x-axis here. So anything that occurs can only occur along the x-axis, along this line, any event that occurs, a flash of light. And so here's an example of a lattice or a grid of clocks along the x-axis. So at each point along the x-axis, I have a clock. Clearly, if I want to specify like halves and tenths and things like that, I just imagine I have a clock at every given tick mark, say, on our x-axis. Here's the origin. Here is the observer. We'll just imagine it's us standing there. We're going to be observing things. And so then here's our grid of clocks. I also mentioned, by the way, in the last video clip that there are 2 different ways of doing this. And actually, we didn't quite get to those 2 different ways in the last video clip. And this video clip, we will talk about those 2 different ways. So if you're wondering what happened to that, this is what's coming up here. So the challenge is how to synchronize those clocks. And so here we are, we're the observer. We have a whole bunch of clocks, and we need to get them at each point along our x-axis, and we need to make sure they're synchronized. So first we'll assume we have a master clock. And by the way, hopefully you did the thought experiment, sort of the priming the brain experiment in terms of thinking about how you might do this, because actually, even though you might think, again, this seems sort of trivial, this was one of the fundamental insights of Einstein that led him to the special theory of relativity, that there were challenges with synchronizing clocks, and it wasn't quite as obvious and straightforward as one might seem. And in fact, this is a case where this was not just some esoteric thought experiment Einstein was doing. These were problems that came out of the electro-technological context of the day, that it was very important as railroads expanded. As railroad expanded, you need to have good timekeeping systems so that every city had more or less the same time, and you had to make sure your clocks were synchronized between various stations and so on and so forth. And there were a lot of patents and inventions, I should say a lot of inventions, that then people submitted patents for at places like the Swiss Patent Office where Einstein was working. So he clearly was getting a lot of this not only just from sort of thinking about esoteric abstract matters of how do you synchronize clocks, but from the technology of the day. It was a key issue that people were trying to solve in various ways. So, whole idea of how do we synchronize these clocks. One way perhaps could be we'll have a master clock, say here, that the observer has, and the observer will bring all the clocks together in one place, and set them according to the master clock, so everything's running just fine. They're all identical clocks. And then move them out along the x-axis at that point. And so that when something occurs, a flash of light occurs over here, and it records it in a photograph, then the observer can be confident that it was the correct time, and this clock is synchronized to the master clock here at the origin. What Einstein came to realize, though, and again later on in the course we'll get into a few more details of this, is that when you actually move a clock, you can't be guaranteed it remains in sync with the original clock. And so even though that method seems like it should work just fine, bring them all together to one master clock, they're all identical, they're all running properly, synchronize them all, and then move them out along to wherever they need to be. In actual fact, it has some potential problems with that, where things will get unsynchronized as soon as you start moving them. Now, what you could say is that we will move them as slowly as we want, such that if there is any unsynchronization, desynchronization that occurs, it's going to be small enough that we won't care about it. So there are ways to get around this, but we're going to use a different method. So this is the first method that, in principle, could work if you're really careful about it, but we're going to use a different method. And this method is, at least we're going to use a different method in principle here. This method is, let's put all the clocks out there, but we won't have them running yet. Okay? We'll just have our master clock here, put all the clocks along, and the idea is that at time t equals 0, we'll have a light pulse be sent along in both directions. So we'll just say, we'll use orange here for a light pulse again. So I guess we used green last time, so we'll use orange this time. So here's the light pulse sent out from the master clock position at t equals 0. Okay? And then as the light pulse goes along my line of clocks here, when a given clock receives that light pulse, or when the light pulse goes by and that given clock is triggered by the light pulse, it will start running. But then you say, well, if this starts at 0 and sends the light pulse out, and then this one starts running when it receives the light pulse, it's going to be behind this clock clearly. So we're going to get around that. We're going to say, okay, if this clock here is 4 units away, whatever units we happen to be using, miles, kilometers, meters, whatever, we know how long it takes light to get there. So we'll say, okay, clock number 4 here, or clock at position 4, we're going to set it ahead just the amount of time we know that the light pulse takes to get from 0 to 4. Now let's just imagine it's 3 seconds. Okay, so it's pretty far away here, obviously, at the speed of light. But we'll say, okay, we know that the light pulse, we know what this distance is, we know how fast the light will travel, and we know that it will take 3 seconds to get to that position there. And so we will set this clock 3 seconds ahead, so that the light pulse goes off here at 0, t equals 0. It's going along here. When it reaches this clock, 3 seconds have elapsed, and if we set this clock 3 seconds ahead, it's not running at this point. When the light pulse reaches it, it will trigger the clock to run, and it will start running at 3 seconds. And then maybe this clock here is, up here, let's see if that would actually be 8 here, 6 seconds ahead. So when the light pulse reaches here, it would have taken 6 seconds from the origin to get there from our master clock, and therefore it would be set 6 seconds ahead, and when the light pulse reached it, it would trigger it and start running. And then everything, assuming we did that with all the clocks, everything would be synchronized. We don't have to worry about any problems with moving the clocks around. All we have to know is what the speed of light is, and then how far away each clock is from my master clock. So that's the idea of how we could synchronize our clocks in theory. Obviously, we're just doing all this as thought experiments, but that's a method we can use to make sure all our clocks are synchronized, and so that for the observer here, once they have their lattice of clocks, they can be assured that any event that occurs, we'll use green this time. So say some event occurs right here, flash of green light, and so we know the position along the x-axis is at x equals 7. The clock will record the time of the flash, and then the observer later on can go out and look at that clock and say, oh, okay, look at the photograph there and say it was the flash was recorded at x equals 7 at t equals 3.8 seconds or something like that. And so again, that's the idea of events, clocks, and observers and how they all fit together and what it means to make an observation. So from now on, when we say somebody observed something, observed an event to occur, what we mean is if we're using just the x-axis here, it's the x location of it and the time recorded on that photo that is taken at that instant in time. So again, the photo clock principle or the clock principle is what we're basing this on. And we're assuming we can synchronize all the clocks by sending out the pulse of light as long as in advance of that we have set each clock ahead just the proper amount. So when the pulse of light reaches it and it starts running, then they're all synchronized with each other that way. Okay, so events, clocks, and observers. And in the next video clip, what we're going to do is look at a different way to visualize how events occur and something called space-time diagrams, which we'll find will be very useful for visualizing some of the concepts in the special theory of relativity.